All right, so we're going to look at the critical points of the surface, f of x, y here. And we've got to remember how we test critical points. Now, to compare critical points and to determine whether these things are local minima, maxima, or saddles, we use what we call the second partial derivative test, which involves the computation of the Hessian matrix. And then we evaluate the determinant. If the determinant's negative, we've got a saddle point. If the determinant's positive, we've either got a minimum or a maximum, and we've got to evaluate the trace to figure out which one we've got. Now, like the ideas behind critical point tests in one dimension, we're essentially fitting a 2D polynomial, a second order 2D polynomial, and we're trying to discover whether we've got this shape, which is a maximum, this shape, which is a minimum, and the Pringles chip shape, if you like, which is the saddle point. All right. We firstly got to find the critical points. Now, the critical points are where the first derivatives are simultaneously 0. So we have to find f sub x, f sub y, the first partials, and set them equal to 0 simultaneously. So let's go about differentiating. Remember, when we differentiate with respect to x, y is a constant. And when we differentiate with respect to y, x is constant. So these two equations now are what we've got to work with to find our critical points. So these things both have to be simultaneously 0. So we got 3x minus y equals 0. That's pretty straightforward. That's going to give us something nice to substitute. This one is going to be a bit more of a pain because we got the quadratic. So this equation here implies that y equals 3x. We can sub that into this equation to get a nice quadratic expression. 6x squared plus 18x equals nothing. So that implies x squared plus 3x equals nothing. So x is either 0 or x equals 3. Minus 3. So there are two values of x. They give rise to values of y by back substitution. So this allows us to identify, we can sort of see where our critical points are going to be in the xy plane. Oops. And the origin. Okay. Now what we got to do is we have to apply the second partial derivative test at the points we're interested in. So we have to work out this Hessian matrix, and then we have to plug in these values of x and y, right? So firstly, note that not all of these combos work, right? It's x equals 0. That implies y is 0. So our first point is the origin. And then the other one is this -3 -9. All right. Okay, so let's work out the Hessian. I need the first derivatives for that. So let's just right, so obviously I have to differentiate f of x with respect to x to get the second derivative. Okay, f of x y, f sub x y, that's going to be equal to, right, the order is not going to matter here. This is it's a continuous polynomial. It's going to not have any naughty points. So I'm just going to differentiate this one with respect to x and get 3. So the easiest thing to do is differentiate that one, but this one's actually pretty simple as well because we've only got the one term that's floating around. All right. So we can collect all of these bits and put them into our Hessian. So we got 12x plus 9. We got -1 down here, got 3, and we got 3. Right. So that's our Hessian matrix. It's only got one dependence. It doesn't depend on y. So the only points we actually have to test are the x points. We don't have to substitute this -9 in. Let's just check to make sure that's all legit. Yup. All right, sweet. We got two ways to do this now. We can either compute the determinant and the trace directly, or we can substitute our points in now and get two different Hessian matrices. That's up to you. The Hessian matrix at the origin is that. The Hessian matrix at -3 -9, -36, -36, what's 16 from 9? That's 7. 27 -27, 3, 3, -1. All right. Yep. Okay, so now we can work out the determinant of this thing. I always like to do the determinant first because that tells me if it's negative or positive immediately. So determinant, remember, you multiply these two and then subtract off the cross multiply of the off diagonal terms. So we get -9 -9. So D is -9 minus. So that's -18. That's less than 0. So the origin is saddle. I don't need to do any more work or thinking about that point anymore. Okay. The next one I got to do is this one. So I compute the determinant. I get 27 -9. That's 18. Now, obviously, that's much bigger than 0. So I've now got to work out the trace. And the trace is clearly negative. So the trace is the sum of the diagonal elements. So these are products, and you subtract the off one. 27 trace of this thing is minus 28. That's less than 0, so I've got a little shape like this. It's a maximum. All right.